So in this video we want to derive the formula for the surface area of revolution for a curve that's been parametrically defined. And all we're going to do is play off the work that we have already done. We saw at the start of this semester that the area of a surface of revolution could be found using this formula right here. So we just kind of want to briefly review this formula. This says 2 pi times r. This is radius as a function of x. R is representing radius. And what we want to remember or recognize is that 2 pi times r, 2 pi r, is just the circumference of a circle. So the surface area of revolution, you take the circumference of a circle and you multiply it by the arc length. This term right here gives us arc length. So it's circumference times arc length to get the surface area of revolution, not volume, but surface area. So what we want to do is look at how we would tweak this if we are in a parametrically defined world. So if x is equal to f of t and y is equal to g of t, and if as x runs over the interval, this is the dx form of surface area of revolution, there's also a dy form of it, but if x is running over the closed interval from a to b, there's going to be t values if we've been parametrically defined. As we saw in the previous video, there's going to be t values running from t sub 1 to t sub 2 that generate the x interval. So that's the first thing we want to recognize. So this is 2 pi times the radius as a function of x. So what we want to think about is if we are taking a curve, a parametrically defined curve, and we want the radius, if we're going to do an x-axis revolution, that's going to make this distance from the curve to the x-axis the radius of revolution. And we want to recognize that this height, or the radius, is just equal to the y-coordinate. And if we're doing things parametrically defined and y is equal to g of t, that means the radius is g of t. So it's very simple. I mean, it's a key thing to keep in mind when you're working is that when you have an ordered pair xy, the y is always just the distance from the x-axis. And the x-coordinate always just tells you the distance from, or the distance with respect to, the y-axis. So we take advantage of that. And then this formula then kind of quickly converts into parametric form because we have the surface area equals, it needs to be 2 pi times the radius. If we're going to run it parametrically, then it's going to run from time 1 to time 2. And we need to describe the radius with respect to the x-axis. But the radius with respect to the x-axis is just the y-coordinate, which is described by g of t. So it's 2 pi times radius to get a circumference, and then times the arc length. But this is just arc length. But in the previous video, we saw that this here can be replaced with a function of t. We saw that arc length is also calculated by x prime of t quantity squared plus y prime of t quantity squared dt. So this would be an x-axis revolution. If we wanted to do a y-axis revolution, so we're revolving with respect to the y-axis, some curve that's been parametrically defined. Well, a y-axis revolution, the radius is going to be the x-coordinate. The distance from the curve to the axis of rotation is x. But if x is f of t, then we simply use f of t to describe the radius for a y-axis revolution. So the surface area formula for a y-axis revolution is just as straightforward. It's 2 pi times the time interval that you need to run over to move things from the start y value to the end y value, and then your radius is going to be f of t, and then you still need the arc length formula, but the arc length formula is going to be the same, right? Arc length is still x prime of t quantity squared plus y prime of t quantity squared dt from the last video that we did. So the surface of revolution formula, and we summarize that here in the next slide, just very nicely converts over into parametrically defined world. X-axis revolution is here, y-axis revolution is here, and it's just 2 pi times radius. 2 pi times radius to get a circumference times the arc length. Circumference, 2 pi times radius circumference times the arc length.